In this video, I will discuss how to derive the flexural strength equation of a reinforced concrete beam. Now, before starting, let me tell you, maybe this is the most important part of reinforced concrete design class. If you understand this video, you are good everywhere inside the reinforced concrete design. So this is the fundamental part of the reinforced concrete. So I will try to explain the derivation very quickly so that I can make the video short. But again, every part of this portion is very important. So let us start with a beam. Say there is a reinforced concrete beam here. There's some reinforcement here. If I apply some kind of load, whatever my load is, hopefully you can see my beam. Yes, you can see the beam. So if I apply different kinds of load, what will happen? This beam will bend. This beam will bend. So if I take a small section here and make it big, so this is that small section. So this is that small section I make it bigger. There's some reinforcement here, concrete here, concrete here. This line is neutral axis. You know that when beam bends, the lower side gets tension, upper side get compression. In middle, roughly middle, not middle, roughly middle, we will get the neutral axis. But again, it's not the middle. It depends on the amount of reinforcement. So this is my neutral axis. Now, in strength of material class, you learned that the stress diagram. The stress diagram is sigma is my over I. So this is stress diagram. Oh yes, let me see let the width of the beam. The width of the beam say B. The width means in that side. In that side. That side is B. Okay, we will need B later, not now. But here, in strength of material class, you saw that the stress diagram is linear, and there is as MC over I, where Y starts from here, or it goes there. That is Y. But when we actually design the beam, we try to apply as much load as possible. So this assumption is valid for linear portion. If my load is very small, if I keep on increasing the load, it is no longer linear. It becomes non-linear. Let me show you. So this is the location of my reinforcement. So if I keep on increasing the load, my stress diagram becomes non-linear like this. So my stress is non-linear, and this portion will disappear. Why it will disappear? Because if I keep on increasing the load, it will bend and concrete will crack, because concrete has very small tensile strength, roughly 8 to 15% of the compression strength of concrete. So concrete will crack. So here there will be so many crack. That is our design assumption. Concrete will crack whenever the stress exceeds its tensile strength, and we assume tensile strength is very negligible. So okay, so this portion is no longer available. So this portion is no longer available. This portion of the concrete is cracked. So again, to tell you, this portion, the concrete around here, has no structural contribution. It is just to cover the reinforcement. So my main concrete here is this concrete, the concrete which is taking tension. Okay, that is a different story. And this depth, you know that we consider this depth C. C means depth from compression or top face to the neutral axis is called C. Okay, we'll go there. This compression block, you can see it is not linear, so very difficult to calculate the area or the volume of this. What to do? We make some simplification. we make some simplification. What is that? We consider it small this. That means we discuss some portion here, and include some portion here. So we make a equivalent rectangular stress block. So this is called equivalent rectangular stress block. So it is better to know this. Yes. So then this one is no longer valid. So this portion is no longer valid. My stress is now rectangular. And what will be the depth? This depth will be 0.85 A prime C. Whatever the max, okay, I deleted that max portion. If I show you, that is again, so that max, this value is A prime C. We are taking 85% of this. So this, the value of this value is 0.85 A prime C. Where we got the 0.85 is just based on research and experience. ACI assumed this number 85%, and if we do the calculation by numerical analysis, we will see that it's 0.85 A prime C. Now this depth is no longer C, because C is up to the neutral axis. This depth we call it is A. It is A. Now you can see A is smaller than C. How to find the value of A? That is a big question. Yes, we will. Now how to find it? So A is beta 1 C. What is beta 1? Beta 1 is a parameter, depends on the compression strength of concrete. Beta 1 we can find it using this equation. If I see your book, so that I do not make any mistake. Okay, so if I can remember that A5 A prime C minus 1000 divided by 4000.05. Let me check again. Yes, I am right. So beta 1 is this. But something else, the minimum value of beta 1 is 0.65, maximum value of beta 1 is max. So remember this. Yes, even this equation is in your FE exam, so it is important to understand. A prime C is your concrete strength. Did I make a mistake? It looks I made a mistake. Here is 4000, here is 1000. Sorry, here is 1000. Now you can see, if your A prime C is 4000, then this will be 0, whole part will be 0. So your beta 1 is 0.85. So the most common concrete is 4000 PSI concrete. So the most common concrete has beta 1 85. But again, this 85 and that 85 is not same, different concept. So this 85 is A is 85% of C. So hopefully you understood what is A, what is C. C is the actual depth of the neutral axis. A is the depth of the equivalent rectangular stress block. So you know what is A, what is C. How to find C to A or C to A or A to C. Whatever it is, if you know beta 1, you can find it. If you know 1. Okay, so story about beta 1 done. Then, I did not show you here. So this is my reinforcement here. So there will be some tension. So this will be tension. T, A, S, F, Y. Why it is A, S, F, Y? Where I got it? T means tension. A, S means area of steel. Whatever the steel I have. So A, S, area of steel. The amount of steel I am using. What is Fy? Yield stress of steel. So Fy is yield stress of steel. So my force taken by steel will be Fy. Where I got it? Yes, simple question. My stress, we know stress is force by area. So force is area times stress. But in reinforced concrete design class, stress we represent by yield stress, and A means area of steel. F is general term, we write T. T means tension. So the force taken by steel is ASFY. So hopefully this part is done. Oh, some part here. No, I think good. So you learn where I am getting the tensile force or tension. Now to be equilibrium, my tension here must be equal to my compression here. So if it is bends, lower side will be tension, upper side will be compression. These two will be equal. So my compression will be here. See, compression. Now what is the value of compression? Similar to this, stress times area. What is my stress here? My stress here is 0.85 A prime C. What is my area? Depth is A, and that side my width is B. So area is, you can write here, AB. So AB is my area, this is my stress. So this, hopefully you understood. A means this, and that side, the width of the beam is B. So this is my compression, this is my tension. To be in equilibrium, tension, compression inside the section must be equal. So if I set it equal, that means T equals C, and that means A, B, is 0.85 A prime C equals AS FY. So A is AS FY 0.85 A prime C B. So we found the value of A. How to find the value of A? This is a very important equation. It is in your FE exam also. At least make a note that you know where A is coming. Do not memorize like whatever I am doing here. You do not need to memorize it. I memorized it because I did it many times. So you know where A is coming from, or at least you know, if you know the amount of reinforcement and the beam size, you can find the value of A. There is an equation, at least memorize that. Okay, the story of A is done. We'll proceed. Okay, now if I take moment here, in this section, so my moment about this point will be force time distance. So inside my section, if I take moment here, then this force will vanish because this force is going through this point. My other force is this force. That force is AS FY. That's my force. What is my distance? What is my distance from here to here? That is the question, right? So, okay, come back. So the depth of, the distance from compression phase to the reinforcement location is called D. So this distance is called D. Entire depth is called ACE. Sorry, I did not tell you earlier, but okay, it is not too late. The entire depth of the beam section is called ACE. The depth from compression phase to the centroid of the reinforcement, again, the depth from compression phase to the centroid of the location, of the reinforcement is called D. So this is D. So my here to here it is D. Here to here is D. But I need here to here. Here to here is D, but I need here to here. So I will deduct this amount. What is this amount? You can see half of A, whatever A, half of this. So my distance is dA by 2. So if I take moment here, force times distance. So again memorize this equation. Now this moment I found what kind of moment is this? It is theoretical moment, whatever my section can take. So theoretical, then we write an n. What does n means? N means nominal. So that is the nominal strength capacity of this beam section. This is how the nominal capacity is coming from. This is nominal. Okay, what else? Okay, something else. So this is the nominal strength. At least memorize this or make a note that you know how to find the nominal strength of a beam. Now, for the USD design, the nominal strength we must multiply by a factor phi. Then it will be my design strength capacity. This will be my design strength. Then whole part will be my design capacity. Design strength or design capacity, both are same thing. This portion is nominal. This portion is nominal. So you learn how to find nominal. Now you have to find the value of phi. That is another story. Okay, we will go there. So at least make sure you understood this. Now I will talk about how to find phi. Phi is strength reduction factor. Okay, I will delete some portion here to make some room. So if I extend this one, now I will draw the strain diagram. Sorry. My strain diagram is linear. My stress is not linear, but my strain diagram is linear. So in this portion, this is C, here to here is D. And so my concrete is here. So here is my concrete, here is my steel. Now this portion is not or does not exist. This portion does not exist. Why? Because we assume my concrete below my reinforcement will crack because it cannot take any tension. So this portion does not exist. So I will delete it. So make your life simple. This portion does not exist. This strain here is epsilon T. That means tensile strain, or sometimes we call epsilon S. Strain in steel, or ET is also okay. This strain is EC, strain in concrete. Now when we design reinforced concrete, we assume that our concrete is about to fail and our steel is about to yield or more than yield. So that is our design consideration. We try to optimize the section, use the maximum capacity of the section. So we assume that our concrete is about to fail, so the strain in concrete is 0.003. And I discussed in my previous video that the concrete fails typically at the strain value of 0.003 or to 0.005, but 0.003 is a very logical number. So we will assume the strain in concrete is 0.003. Now if I use the similar angle triangle rule, so this is a triangle, this is another triangle. So or we can do other. Okay, so we know this portion is C, this portion is D. So here to here will be D minus C. This portion will be D minus C. So this triangle, if I take this triangle, epsilon T divided by D minus C, that means this side by this side must be equal this side by this side. So 0.003 divided by C. Then epsilon T equals D minus C 0.003. Yes. So this way we can find the value of tensile strain. Value of tensile strain. Okay, let me check the question in the book whether it is right or wrong. Yes, it looks it is right. So I'm just checking with book so that I do not mess up anywhere. So this is the value of the tensile strain. Now why did we find this, or why I did it? Because can you remember we are talking about this strength reduction factor. Strength reduction factor depends on the tensile strain. Depends on the tensile strain. So we will discuss it, but before that make sure that you know how to find the tensile strain. Okay, so I will make some room here. Now phi, let us talk about phi. According to ACI, so phi value depends on tensile strain. Minimum value is 0.65. After some time it goes up and then becomes constant, and this value is 0.002, and this value strain value 0.005. This value is 0.9, this value is 0.65. So you can see here, if my tensile strain is 0.002, my phi value is 0.65, or if it is less than this, 65. If my epsilon t is 0.005 or more, it is 0.9. So whatever the value of epsilon t, if it is here or here, you got an answer clearly. What about if your value is somewhere here in the middle? Then you need to use this line. Now if you see the new edition book, 10th edition, maybe they used here some other value, 0.0027, but that's not a problem. Or they might use other value like, let me write it, epsilon y t maybe. Epsilon y t means yield strain in tension. That means yield strain of reinforcement. Okay, again, if people or different book use different value for this, don't worry, it is the yield strain of steel. The concept is my steel must yield. If it doesn't yield, it is here, low factor. Now how to find this? Simple, yes. You know the equation, stress is modulus times strain. Then strain is stress by modulus. You saw this equation in strength of material class, strength of material. So here you will find it, our yield stress divided by the modulus of steel. So if we use 60 ksi steel, that is the most common, so 60 ksi, and our it is psi. You know that whatever the strength of steel is, the Young's modulus is 29,000 ksi, or 29 to the power 6 psi. We know this value. So if I solve this problem, mathematics, I got 0.00207 here. 0.007207, yes. So 0.00207. Okay, make some room here. That is the yield strain of steel. Okay, maybe I was lost. Oh no. So I need to find what is the value of phi here. So the value of phi here. How to find it? Different ways. Maybe I do not need it anymore. Or make some room here. how to find phi when my steel is in between. So if you use your old book, I have the book here. If you use your old book, the equation is 0.65 plus epsilon t minus 0.002 250 by 3. If we use the new book, 10th edition book, you will see other equation. That equation is 0.65, 0.25 epsilon t minus epsilon yt 0.05 minus epsilon yt. Okay, delete it here. Okay. So this is in your old book, this is in your new book. If we use the FE reference handbook, they use different equation. If I can remember correctly, let me see one more time. It is 0.4883 epsilon t. Now epsilon yt is the yield strength of concrete, steel. So it is in 9th edition book, it is in 10th edition book, it is in FE. So whatever book you follow, doesn't matter, your answer will be very, very similar. In your FE exam, you will use this equation. If you use 9th edition book, you will get this, 10th edition this, but this one is the most recent and most accurate, but no problem, your value will be very close. So whatever equation you use it. Okay, so hopefully you understood what is after. You understood everything here. I will delete. Now some discussion here. What is the meaning of this? Meaning of this is tensile strain in steel is 0.002, that means just yield. Below this means my steel did not yield. So in my section, this is my section, if your steel does not yield, then my failure will be here. That means it did not yield, so concrete might fail. So this reason is called compression control. Compression control. This reason, that means my steel did not yield, failure will be in compression. So this is we do not want it. Why? If concrete fails, it fails suddenly because it is very brittle material. Brittle, it will fail suddenly. We want concrete will not fail. We want steel will yield. If steel yields, what is the good news? Steel is ductile. It will yield. It will be like it will be elongating. We can see my beam is deflecting. We will get some time to vacate the room if it fails. But steel will give me some warning. But concrete will not give. So we do not want this. This portion here. So if I draw the stress system diagram, is still 0.005 means roughly here. So roughly here, that means here, if it is here, my steel will yield. Concrete will be in good shape. That is safe. So we want concrete to be in good shape, steel to yield. So this area is called tension control. So this area is tension control. In between is transition. So we will discuss more about it. So we do not want compression zone. We want steel to yield and concrete in good shape. Here is in between, but this is a beta zone. We want this area, and up to 0.004 is okay. In most designers says 0.004 is okay, but no way close to or less than 0.004. We will discuss more. So if I summarize, the nominal strength of concrete is A is Fy D A by 2. If I want design strength Mn, I will multiply my factor A by 2. How to find phi? To find phi, you have to find A first, then beta upon first, then C, then epsilon T, then you will find your phi. How to find A? A is Fy, find F5, F prime C, B. This to find A. How to find beta 1? There's an equation minus A prime C divided. There's an equation. I have no space here. So there is an equation, but simply it is 0.85 to 0.65 to 85. Then find C. C is A by beta 1. Then find epsilon T. How to find epsilon T? I just discussed earlier. Then find phi. Once you find phi, you can use it here. A is reinforcement area. Fy yield stress of reinforcement. D depth from compression phase to the centroid of the reinforcement. A is here. So hopefully you understood the flexural strength equation. This portion is very very important. If you understood this part, the rest of your life in reinforced concrete will be very easy. So today I will stop here. In next video we will start designing a beam. Thank you.